Coming up next, we have a series of Quickfire talks. And a Quickfire talk is a short 15-minute talk from an up-and-coming company. And these have much promise. And so we have 3 of them. And the first is with Michael Hurowitz. He's the co-founder, chief technology officer, and senior vice president of engineering of Orbital Microsystems Incorporated. He hails from the Colorado School of Mines with a Bachelor of Science degree in engineering physics. And he's also an instructor at the University of Colorado Boulder. So I'd like to introduce Michael Hurowitz.
Good afternoon, everyone. Thank you so much for your time. Thank you for the kind introduction. Today I'm going to tell you a little bit about Orbital Microsystems and the platform we're building to deliver weather intelligence for the world's decision makers. So a little background first. So today, Air Force and commercial pilots take off with weather data that's at least 6 hours old. In the commercial world, there's about $2 trillion in pent-up demand for insurance globally, much of which is those markets aren't able to be entered because of a lack of data to build accurate risk models, sort of the beginning of the process. And in our work with Lufthansa Systems, they've estimated that with better use of real-time weather data, they could reduce fuel costs by as much as 20% for global airlines. So pretty big set of problems to tackle. So our company set out to commercialize a low-cost passive microwave sensor that we've developed in partnership with the University of Colorado. These sensors are critical for letting us look inside storms and build 3-dimensional maps of temperature, humidity, and precipitation. You can see on the left, from the same instrument, we get 4 different vertical slices of a storm, starting the upper atmosphere and penetrating deeper into the storm. So we can see where the rain bands, the precipitation are, and help optimize the response, as well as use that information to drive forecasting models, project where that storm is going to hit. To date, these have been very expensive platforms. $122 million was the development cost for the advanced technology microwave sounder flying on JPSS. We're still depending on a lot of heritage instruments from the DMSP program and MedOps. As you can see on the left, microwave sounders actually have the single largest contribution to forecasting skill of any sensor type, followed by infrared sounders, both of which are 3-dimensional profiling instruments. So it's not a high-resolution system, but is actually building a temperature and humidity map that is used to drive numerical weather forecasting. So we're actually facing a reduction in the total number of operational instruments as we lose the DMSP satellites over time. So our proposed commercial solution, the Global Environmental Monitoring System, or GEMS, is a constellation of cube satellite-based microwave radiometers using frequencies at 89 gigahertz and above to do spectrometry of the atmosphere. We use 2 key resonances of oxygen and water vapor at 118 and 183 gigahertz. They'll actually retrieve a vertical profile, and that produced, after going through the various processing techniques, results in a 3-dimensional temperature humidity cube. And there's also a sensitivity of the instrument to rate and type of precipitation, has a strong impact on the absorption and scattering. And so from that, we can actually see what kind of precipitation is it and how much is falling. And with a fleet of these, we can see that with better temporal resolution than we've ever had before, which will enable some pretty cool advances in the forecasting technology. We also have a technology developed with our partners at National Snow and Ice Data Center we call Weather Record, which is an on-orbit anomaly detection based on the condensate algorithm. And essentially, this will rapidly screen large gridded data sets for quality assurance and anomalies, and we can then apply parametric triggers on top of that for our customers, so we can tell you if there are frost conditions detected or if a temperature exceeds a certain bound. That's completely up to the customer and geographically and what type of thresholds they would like to set. This can be applied on terrestrial sensors as well, so that's part of our bag of tricks. We've also been working for about 20 years now, actually, on weather lock concept as a precipitation-locked weather model, where we're comparing a real-time set of observations from the satellite against what the model has actually predicted as what we should see. And so by doing so, we can actually drive that model in real time and correct for the errors as they have propagated through the model. Much easier said than done. But even with our passive microwave data and addressing a large number of weather challenges, we still run into some pretty significant barriers in our attempts to penetrate other industries with other types of products, and really boils down to the fact that really complicated analysis like weather forecasting or flood risk modeling or insurance risk modeling requires multiple sensor types. You can't go it alone with one type. But historically, sensors don't share a common format in time, space, or with the data type. And so the impact of that is, in many cases, the sensor fusion process takes longer than decision makers can afford to wait, and opportunities are lost in the process. So we have this fundamental need to achieve sensor fusion at the speed of human systems. So today, this will be the first actual public introduction of our efforts on the International Center for Earth Data, which is going to be is in development now. A team of scientists from around the world are meeting as we speak to develop this architecture that will combine public, private, and military data sources in near real time to allow analytics to flourish. It's been one of the biggest barriers to acceptance of many different applications of satellite remote sensing data over the past several decades. And we're actually able to work with the Air Force, the Royal Air Force, Lockheed Martin, and a number of corporate data providers and analytics companies who all share this common need. And it will also help reduce barriers to entry for companies that want to get into either the analytics or the space remote sensing business by providing a common ground infrastructure that make their data available to their users. So this is a consortium, a private-public consortium. The University of Edinburgh and the University of Colorado are key partners, along with OMS and several corporate partners. And then you can see the ring around the core is data providers for visible, IR imaging, ICI, and Astra Digital are partners as well. So bringing radar systems, bringing Landsat equivalent sensors, and then about 2,000 analytics companies globally that build various environmental analytics stand to benefit from this. And now we're going way beyond just weather and addressing needs for analytics in a whole lot of different industries. As you can see, it's a broad range of potential applications, some of which are well developed, some of which have a long ways to go. So this we hope to create as a new customer experience where you can come to this platform and get private data, public data, and the data we provide through our passive microwave, we expect that to help the platform be sticky because that's a unique data set that isn't available anywhere else. Putting it all together in one platform and letting you do analytics right next to the large data sets in the cloud enables basically three classes of users. There are subscription-based users who are what we call advanced users who already run their own models and just need the data feeds. There are also subscription products that our analytics partners will develop. And then there are sort of pay-to-play type of reports that can be generated as well for, say, a risk model or a historical analysis. So what makes this different? This is really going to be a marketplace when it's all built. The focus is on speed and reducing the latency in the sensor fusion process, making sure that the data is available when it's needed. The data providers will own their own data and set their own price. So we're not going to try to take other people's data. They own it. That's one of the perks of this platform. It's focused on business users and producing analytics-ready data. And the same for the analytics sides. Analytics companies will own their own analytics and set their own prices. And the marketplace will help to figure out what price can actually be supported. This is one of the open challenges in commercial remote sensing still, even after 20 years of visible imagery, is how to price it right for the market without kind of pricing yourself out of other markets. And most importantly, the coincidence of data is one of the big challenges, making sure it aligns in a common format and projection so you can actually work with it. And with customers involved in the process throughout the entire development to make sure it's actually addressing what they need. So let me give a few use cases for this platform. So what happens if we have a major hurricane in August of this year? Well, the microwave data that OMS produces will provide risk transfer information to catastrophe bond markets, insurance markets, and help first responders make sure they're using their resources wisely. While our partners at ICI will use their synthetic aperture radar technology to do flood and landslide monitoring that can be tasked by the passive microwave to make sure they're looking at which situations are going to be most severe and also helping optimize the response. And then Astra Digital can come in with their Landsat equivalent and provide pre and post data for event damage and analysis. So, all these different sensors come together to really help solve a crisis situation. In the commodities market, in 2012, there was a major crop failure in Russian wheat that led to soaring prices for wheat crops around the world. And the commodities brokers, the farmers, strategic planners, the people doing logistics all stand to benefit, but they need that data in minutes in order to offset risks. And they need more than just microwave. They need imaging. They need SAR systems, ground-based weather radar. And the result of that is we can apply a lot of different types of analytics, many of which these algorithms already exist, but without the input data, they only can solve so much of the challenge. So thinking of crop damage or flooding and drought situations that could be analyzed in closer to real time. In aviation transportation, this is from June of this year, just a couple weeks ago. We're lucky that this plane made it home safe. You can see the damage from hail to the windshield. The pilots did their best with the available information, but it was outdated, and they're relying on in-flight instruments, which have a limited range. And with a 6-hour-old weather report, you just can't. The atmosphere's natural rate of evolution is around 15 minutes, so you just can't see it without a real-time look at the problem. So we can provide 15-minute anomaly detections to the aircraft pilots, the ship captains at sea. These are major subscribers. Anyone operating a maritime or an airline will benefit from this type of anomaly detection. And the analytics, we can, with our precipitation locking technology, give a better forecast to begin with. We can also tell you, is this hail or rain or snow? Is it freezing? What about winds? And pairing in public data from NASA and NOAA that a taxpayer is already paying for that infrastructure, but in a lot of cases we're not able to actually use those sensors. We can get more details on the storm cloud height and intensity, ocean winds, and anything else that might be required in near real time to make sure that airplane takes the safest possible route. And the really exciting part about ICE is that this is a cloud-based platform that can be dropped into the military cloud. So we are working with the Air Force on they're actually participating in the workshop this week. And here we're going to provide advanced analytics for theater operations, and they can then also bring in classified data sources to drive this real-time decision-making effort that they're needing to support ground forces, support the aircraft, know what are the conditions over our target, what about communications links. Even just the change in presence of humidity can lead to a degraded link, especially in the case of optical communications. So there's a lot of analytics that can also be applied. So the real goal of this platform is to enable all of this real-time decision-making that today is very difficult to achieve, and in a lot of cases just can't even be done. So today we have achieved global traction. We have set up a second business in the United Kingdom, so we are a international small business. We have 2 satellite missions booked as demonstrations, the Polar Cube mission with the University of Colorado, and an in-orbit demonstrator with the Catapult satellite applications in the UK. Working with Clyde Space and the UK Space Agency, a couple other projects that will be announced hopefully in July. We've got a strategic investor in Lockheed Martin and a financial investor in Kairos, about $6 million on the table for our Series A, and we're trying to get 3 to 5 more. So if anyone is looking for investments, we'd be happy to talk, but we're very close to closing that Series A. We have letters of intent with multiple customers, and we have a strong partnership for the International Center for Earth Data, so really making a lot of progress on all these fronts. And so how the heck can we possibly do all this? Well, we have a team of people with 235 years of collective experience in multiple industries, from consumer electronics to mining to aviation to scientific research and instrument development for NOAA and NASA, running a data center for NASA at National Snow Ice Data Center. So really it's the team of people that makes all this possible, and we wouldn't be here without having pulled this all together. So, all right. Thank you. Do we have time for questions? All right, one question.
Are you building your own spacecraft? Are you secondary payloads? What's the strategy?
Secondary payload is a challenge for us just because of the actual systems engineering requirements for pointing and altitude and things like that. So we build payloads, but we're working with partners on the integration and spacecraft bus. Doesn't make sense to reinvent that wheel. Okay, thank you.